Quantum physics is a truly mind-boggling subject, but it all comes from the basic understanding of a particle and a wave. This marble is like a particle. When put on an axis, it has a single definite position at any instant in time. Waves, on the other hand, are disturbances in the medium. When put on an axis, a wave cannot be assigned a single position and is at many different places at the same time. Now, quantum physics tells us that all matter in this universe behaves like both a particle and a wave. So, how exactly is this possible? How can we be both sure and unsure of our position? To understand this, let's conduct a thought experiment. First, close your eyes. When you can't see me or hear me, there is no way of knowing where I am. In which case, you cannot assign a position to me with 100% certainty. Instead, what you can do is predict all the possible positions and the probabilities of finding me there. For example, I can be 90% at home, 1% in Paris, and 0.001% in space all at the same time. Like this, I can be anywhere and everywhere in this universe simultaneously. So it seems that I behave like a wave by being in many places at once when not being observed. But this is no ordinary wave. It is a wave of probability, of how likely I am to be at a particular position. But what happens when you open your eyes? Suddenly, all these positions collapse into one, and I start behaving like a particle, by being in only one place at a time. What happened, you ask? The act of observing collapsed my wave function. This wave-particle duality applies to everything, from electrons to human bodies. But if that's the case, why aren't there multiple versions of us when we're not being observed? The answer to this lies in our wave function. Wavelength is very important to the wave function, since a large wavelength implies a greater range of probabilities and a short wavelength implies a shorter range. And due to this correlation between momentum and wavelength, we know that very heavy or very fast objects have a very small wavelength. An average human, for example, has a wavelength of 5 into 10 to the power negative 36 meters, which is far too small to ever detect. So, although quantum superposition exists for objects we see every day, their wavelength is simply too small that its effects are negligible to the human mind. Electrons, on the other hand, are much smaller, and thus have relatively larger wavelengths that have been experimented with. These experiments, in turn, have given rise to the mysterious quantum realm. From here, you can explore quantum consciousness, quantum entanglement, Heisenberg's uncertainty principle, quantum erasure, and many more exciting theories. Just remember that it all began with a particle and a wave.